Hello everyone, I'm Zhipeng Zhang. Today I'm going to introduce the work we have done on training generalized linear models using Spark MLlib with very old tricks. So about 5 months ago, our friends from Oracle gave us a homework, and the question they were asking is, how fast can you run machine learning on Spark? And as to react immediately, almost as his second nature is, why do you guys even want to run machine learning on Spark? It's not really a crazy question to ask, because if you look at the recent papers published in Sigmod or VeroDB, you will find that most of them are talking about tens or hundreds times speed up over Spark. Most of them are using a different system architecture from Spark. For example, dim-weighted run on multiple cores with a single machine. Petum and Angel use parameter server. Even those people who build Spark, they introduced the asynchronous execution model for Spark. So with all these papers taking advantage of execution model beyond Spark, it's quite natural to ask, can Spark really be able to run machine learning efficiently? We decided to look into this case because our friends from Oracle made a pretty good case. When the data from the user is already locked in Spark ecosystem, then Spark's default machine library is one of the most popular choices. So here in this talk, let me share with you some real quick lessons we have learned during this exercise. So the first lesson we learned is that machine learning on Spark can be much faster. As we will see, it's quite easy to get a version of Spark that is 240x speed up over MLlib. The second lesson is that the optimized Spark MLlib can achieve comparable and sometimes better performance with those specialized machine learning systems, such as Petum and Angel. The third, and probably the most surprising one, is that none of our optimizations are new. The youngest technique is already 7 years old. So the conceptual lessons we have learned is that the community needs a stronger baseline for distributed machine learning systems. And before we start building the next machine learning system, we should read some really good and old machine learning papers carefully. Now let me tell you what we have done. So Spark MLlib uses stochastic gradient to train generalized linear models such as support vector machine or logistical regression. Given a loss function like this, here A is the data point, X is the model, and B is the label. SGD can be used to solve a optimization problem like this. So here's the game. We can see that there are 3 players in this game, like data source, computation device, and storage device. When doing SGD, we first read the data from data source and load the model from the storage, and then we use FPGA, GPU, or CPU to calculate the gradient and update the model. If there are multiple machines, then we periodically average the model among all the machines. So this is a figure about how SGD is implemented in MLlib. Suppose you have several executors and one driver. The driver will first broadcast the model to executors. Then the executor computes the gradient using the model and the local data. The driver will collect the gradient and sum it up update the model. As we can see from this Gantt chart, we can find that the bottleneck of this process is that the cost of communication dominates the cost of computation. There are 2 reasons. The first one is that we can only update the model per communication because we are sending the gradients over the network. The second reason is that lots of executors are just waiting for the driver and doing nothing when the driver is collecting the gradients or updates the model. So we used 2 tricks to deal with these 2 problems. The first one is model averaging. So rather than sending the gradient over the network, we do local SGD inside each executor. Then the driver collects the gradient, collect the model, and do the average. This can greatly reduce the number of iterations for convergence because in this case, each update, each communication will contain much more updates to the model. Second, we use a more balanced communication. Rather than using tree aggregate, we adopt a reduced scatter rate for communication. Suppose you have several models, you first split them into small pieces and then shuffle such that each executor is only responsible for one small piece, and then do the average and broadcast it to all the executors. If we look at the Gantt chart, we can find that none of the executors are spending long time waiting for others. So we did some experiments to validate our optimization. We run linear SVM on a cluster of 9 machines in 1 gigabit network. These two figures are results for different systems on some dataset. Here, MLlib star means the optimized version of MLlib. As we can see, MLlib star can get 21x and 240x speed up over MLlib with and without L2 regularization. Also, we can find that MLlib star can actually get comparable and sometimes even better performance compared with specialized machine learning systems such as Petum and Angel. So before declare victory and move on, let's think carefully what could be the potential limitation of our optimization, and can we use more tricks to improve it? So here is the problem. If you have too many machines and each machine don't just have a very small partition of the data, then model averaging becomes almost SGD, and it could need more iterations to converge. And what can we do? So one lesson we learned from Spark guys by bragging our results to them is that they are implementing a new version of LBFGS in their Spark. And they think LBFGS is actually slow and faster and scales better than SGD. But is this true? Well, if you compare their implementation of LBFGS with MLlib star, in many cases LBFGS is actually slower than MLlib star. But we do observe some cases that LBFGS can converge faster and have a better loss. This is not surprising, and this essentially shows the trade-off between first order and second order methods in mathematical optimization. To get the best of both, we tried out a hybrid approach to benefit from both. We first run model averaging and switch to LBFGS when we get enough improvement from model averaging. This gives us a very robust method such that we can get a performance close to the best of MLlib star and LBFGS. Want to guess how old is this technique? It's 2011. So this is a very quick summary of all the tricks we have played so far. If there's only one message you are going to remember, we hope it is that the machine learning systems you are using every day might not be as well optimized as you thought, and the answer of making them faster may just be hiding in a pile of old machine learning papers, waiting for us to rediscover. Thanks.